This is 1997, number 88. So how do you do this? There's an easier way and a harder way, and I'll probably show you both. So this was a area function, right? If you look at it, whatever value of x you plug in here, that x is that x. And basically it's the net area from A to whatever value you plug in there. So where h is the graph above, so this is h of x. And so A is over here. Here's A. So whatever value I put in for x, like say I put in 0, I would integrate from A to 0, which would give me the net area of that piece. Okay? So as I move, if I start at A, and I put an A here and an A here, what's the integral from A to A? Clearly it's 0, right? So if I started A, this function will be 0 because the net area from A to A is 0. So it has to start at 0. That's 0. This is starting at some value. I don't know what that is. That's starting at some value. So your only choices now are A and E, because the value at A is negative. The value at A is positive. The value at A is positive. But when you plug in A here, the area from A to A is 0. So we can eliminate anything that's not 0 at A. Now we have two choices. And this is where it gets tougher. And I will explain how to make it easier on you. So we're going to evaluate it the harder way. So as I pick different values and I move across to the right, the area of the region is going to keep getting bigger and bigger. So let's look at the areas of these chunks. So that's approximate area. That's bigger area. That's bigger. That's bigger. So as I move across, I keep adding bigger and bigger chunks. If I add bigger and bigger chunks, the function should increase faster and faster. Okay, now look. Here, it increased a little bit, then more, then more. Do you see on each little interval? I need a smaller pen. Let me do this with a smaller one. So if I go over, it goes up a little bit. Over, up more. Over, up more. Do you see each of these? You keep on adding bigger chunks. Now, if you look at this one, at first we go up a lot. Then we go up just a little. And then we go up a tiny bit. So each time you're increasing less and less. Here, each time you're increasing more and more. Which one fits better if you look at the area? Each time, are you adding more each time or adding less? Your area keeps increasing by more each time because these rectangles keep getting bigger. So it fits this one where you're adding more each time. So that would be the correct answer. Now, here's an easier way to do it. So for those of you who like seeing easier ways, check this out. Are you ready? I can take the derivative of this. F prime of x equals h of x. This is fundamental theorem. If I take the derivative of both sides, the derivative of an integral from a constant x, you just plug x in, right? So technically, this is f prime of x. Hello? And these are f of x. Right? Okay. So let's look at this. What's the derivative at b? What's the derivative right there? Does not exist, right? Because it's a sharp point. So the derivative should not exist. Here's the derivative. What's the derivative at b? It's 0. It's on the x-axis. Now let's look at this one. What's the derivative at b? 0, because the slope of the tangent line is 0. So e fits better because e, the derivative is 0 at that point. And so you could look at this, if this is f prime, because we calculated that, we took the derivative of both sides. If this is f prime, it's positive from to there, so my function should be increasing from a to b. Is this increasing from a to b? Yes. Is this increasing? Nope, decreasing there, doesn't work. Is this increasing? Nope, decreasing there, doesn't work. Decreasing, doesn't work. So that's increasing from a to b, that's increasing from a to b. So now we know that works. From b to c, it should be decreasing because f prime's negative. Is it decreasing from here to here? Yes. Is it decreasing from here to here? Yes, that fits. The derivative changes from positive to negative there. There should be a relative max at b. Relative max at b, yes. Relative max at b, yes, that fits. So the only thing that really distinguishes it using this one, and there's actually another technique I'm going to use just to blow your minds a little bit more. The fact that this graph does not have a derivative of b because it's a sharp point. And this one, there's not a hollow point. There's actually a dot at b. Therefore, this doesn't work. I'm going to give you another way, okay? And I know it's not asking for this in this, but it's going to help you overall in the test. Here, I claim from here to here, f prime is increasing, right? This is f prime, and it's increasing from there to there. I didn't mean to write that. It's increasing. What does it mean if a function is increasing? That implies its derivative is positive. That means the second derivative is positive. If a second derivative function is positive, that implies the function is concave up. Which function is concave up from 0 to a? That's concave down, no bueno. That's concave up, mucho bueno. So again, we're coming to the conclusion, it's E. There's a lot of ways to look at that. And I think it's easier by looking at the derivative and the second derivative and getting information from that. So that's why some people will answer that a lot easier than others, because they look at it in different ways.